It's very nice to see that the audience is quite high after this very nice banquet. And I think the organizers succeeded to have a very nice dinner with this wonderful atmosphere. And today it's my honor and pleasure to chair the session, and with the plenary lecture of Kiyoshi Ueda. And it's fantastic to see when you have a quick look on the CV of Kiyoshi. Kiyoshi was already detected as a future star at his thesis in '82. He defended his thesis, the PhD thesis at the University of Kyoto, and he directly obtained his permanent position at the University of Sendai, where he became full professor. And he is now emeritus professor at Sendai, and also he obtained the fellow of the University of Sendai. He is now adjunct professor at the Shanghai Tech University. During his career, Kiyoshi his scientific interests were on the ultrafast dynamics, and mainly on atoms, molecules, clusters, nanoparticles, and he was mainly using synchrotron and FEL, but he also has a huge interest with ultrafast lasers. Kiyoshi has been invited professor in many places, England, France, in our group during the 90s. I had the pleasure to become friends with Kiyoshi at that moment.
When we were very young.
Now he's invited professor regularly at Zurich in the group of Hans Jakob Werner. He just arrived from Canada. He was invited professor in Berlin. Kiyoshi is everywhere. And he has been a co-author of more than 650 papers with a very impressive list of high impact factor journals. Kiyoshi is experimentalist, but he can also work hard with theoreticians to push them to the limit. This is very impressive. And just to let you know, the committee, the international committee, is so impressed by Kiyoshi that is now honorary members of the international committee. It was decided on Monday. So I think the audience is impatient to listen to you, my dear Kiyoshi.
Thank you. Thank you very much, Mark. And it's really my pleasure to give this talk on this conference. I have been in this conference more than 30 years. So this is one of my hometown. And I feel very honored to give this talk as a plenary speaker, and I feel very honored that I was now, what do you exactly say? I mean, honorary member, right? But honorary members, the retired person, right? But anyhow, the title means that what I wanted to do in my career for about 40 years. This does not mean what I could do. And as he said, as Mark said, after my retirement, I was trying to enjoy my retirement, traveling around, but the COVID started. But still, I could go to Zurich, thanks to Hans Jakob. I could go to Berlin, thanks to Mark Wacking. By the way, Mark Wacking is a vice chair of this conference, but he's organizing another conference in Berlin. And now I'm visiting Canada, and Francois Regard is hosting me. This is really the situation of fantastic my retirement. And this is what I'm going to talk. I mean, I'm basically a scientist of XFL. Historically, I can show you when I entered FL business in the next few slides. And then I will start introduction to XFL science, but that could be very short. And then as a first example, I wanted to show what kind of experiment could we could do with hard X-ray XFL Sakura. The photon flux of Sakura is, I must admit, more than one order smaller. And if we talk about the photon density, 2 orders smaller than L3S. What can we do? I will show what we can actually do with Sakura, and then I'm going to talk about European XFL experiment. But the main dish on that subject will be given by Till. I'm just giving an introduction of his talk. And another field I loved was Fermi. And I'm going to show, because of the performance of Fermi, we can really steer the electrons. That was really completely new for us. People, until Fermi arrived, people haven't thought about this possibility. I really wanted to emphasize it. And usually I put one experiment from LCDS, but in this conference, there are 3 people from SLAC, and including John Marangos, there will be 4 talks. I will completely skip LCDS experiment. But on the other hand, I'm very happy to introduce some experiment I did together with Hans Sakub's group. This is direct relation to the 4th subject. You can see the connections between Fermi experiment and the lab experiment we did together. Okay, this is the history of the FEL. The first FEL is Flash. It started user operation in 2005. And then LCS started user operation in 2009. But just 1 year before, we got a test facility in Japan. That is 2008. It provided fully coherent helium lamp. I mean, the photon energy is 20 electron volt. But this is how I started a FEL experiment in Japan. And we got Sakura in 2012. That is hard X-ray machine. As I said, the photon flux is more than 1 order smaller. We really ought to think what we can do with Sakura. And my favorite Fermi started operation in 2012. And more FEL coming out, especially in 2017. There are 3 FEL started operation for users. One is European XFL, the other one is Swiss FEL, and the last one is PAL XFL. And last year, Shanghai completed they tested seeded FEL and commissioning is finished. Now they are commissioning the beamline. So it's really coming up. And already at the same time in Shanghai, all the funding for making hard X-ray high rep rate machine is approved, and they already started construction. This is really the situation. That's the reason why I have to go to Shanghai. And why people want to have XFL? That's because of the character of the pulse. The pulse is coherent, intense, and ultra-short pulses at very short wavelengths, from XUV to X-rays. And because the light is coherent, one can use this light as a coherent imaging on non-crystallized sample. But this was exactly the same idea of low emittance synchrotron, as you already seen here at Sirius. So basically, having coherence, it is not very necessary to have crystals anymore. That was really the idea behind. But in the case of FEL, the pulse intensity is so strong, so whenever we record the signal, the sample blow up. So the idea is to record the information before it blows up, so the pulse duration should be within 10 femtosecond. This was what people believed. And that's the reason why Sakura has a pulse duration of 10 femtosecond, in fact. And actually, in the first round of LCDS, they demonstrated it works, but this is just a single shot. So within single shot, they tried to extract the information, 2D information. The reason they could get only single shot is because single shot completely damaged the detector. So it was really a single shot experiment. And then data basically ties demonstrated that adding giant xenon cluster together with this kind of molecule, she did photography, and then she could extract 3D imaging within single shot. That was one of the breakthroughs in this field. But if you notice, I mean, the resolution they can reach is still something like 20 nanometer, far from atomic resolution. And if you compare that resolution of cryogenic electron microscope, you have to think which is better. I mean, I don't want to be critical, but this is what people started to argue. And the reason why people want to have X-ray is, of course, to get atomic resolution. And still, in order to get atomic resolution, we need crystal. That is really the situation. But the crystal size can be very small, nano size. That should be okay. We don't need to make a big crystal. And again, in the first demonstration, they injected nanocrystal and shine it and took the data. And if you see so-called small angle scattering data, it's X-ray scattering now. If you see small angle scattering data, we can reconstruct the structure of the nanoparticle. But if you see wide angle scattering, we started to see the structures. And the demonstration is by 2 kilovolt photoenergy, and the resolution is 22 nanometer, so it does not have any atomic resolution. But once they got hard X-ray, they immediately reached the atomic resolution and started to solve new structure. This brings us the first subject. So catching atoms in action in nanoparticle by X-ray diffraction at Sakura. Sakura started operation in 2011, as I said. No, it raised. And we had to go and see what kind of light they have. And when we went there, before the experiment, we were on TV. And what we had to do first is that with the condition of single-shot imaging, what will happen within 10 femtoseconds? This is what we worked on first, using experiment and MD simulations. And of course, I mean, in a sense, the result was clear. All electronic dynamics, charge build-up, redistribution takes place within 10 femtoseconds, but the explosion of the molecules are certainly above 10 femtoseconds, up to 1 picosecond. We could identify all those numbers for atoms, molecules, and nanoclusters, and then, but what we really wanted to do is time-resolved structural dynamics. That means time-resolved X-ray diffraction. And we addressed two things, crystallization kinetics and ultra-fast electronic and ionic dynamics. That means plasma dynamics. Because if you hit nanoplasma by intense laser, it really becomes plasma almost immediately. And we wanted to investigate that. So the experiment looks very simple, but technically it's not at all simple. We just inject big xenon clusters, and the size of the clusters should be something like 10 to the 7th atoms. We did the calculation with the intense of Sakura, and unfortunately, this is the number we need to do the imaging. So this is the reason why we have to make such a big clusters. And the size is 16 nanometer or something. Then we can do the imaging. And we do wide angle diffraction because we wanted to know the structure of inside the cluster was inside the nanoparticle. So what we wanted to see is the following. From the order we know, depending on the size of the cluster, the crystalline structure seems to be different. So if the size is 10 to the 5th, then it was stored a mixture of FCC and HCP, and if it becomes bulk, it should be FCC. And so just for the beginner, or just for people who may not know what is FCC and HCP, and FCP is face-centered cubic, so the structure is ABC, ABC, ABC. And HCP corresponds to hexagonal cross pack, that means AB, AB, AB. That is the difference. And we just accumulate the data, and then this is what we see. This is powder diffraction. So many, many, many shots. And you can see the peak of FCC 111 here. It is, in fact, a mixture of HCP 002, but we know this is very small. But we notice there's a very broad peak here. This is supposed to be HCP, but something's wrong. It's broad. So because it's broad, we can have a chance to detect angular correlation of this black spot. By detecting this within a single shot, two black spots within a single shot, we can measure angular correlation. And measuring angular correlation, we can actually start to see the structure. And we do the fitting, and the reason why it is broad is because in the reciprocal space, the black spot is very long. So basically, this becomes black dots. So by doing the fitting, we know this distance. And the result was the following. If we do the fitting, we can get this number, 0.59 per angstrom. But if we assume complete random RPCP structures, the expected value is 0.6. So basically, it is clear that the broad peak is the signature of RHCP. Then why do we have RHCP? One more thing we have to be sure is that we really want to know single crystal. So far, the data did not tell it. So we really have to do single shot imaging, and this is the result. And it should be lucky because we cannot align the nanoparticle. We really ought to be lucky, and if we are lucky, the nanoparticle is in the right direction, and then we see streaking. So we have very strong FCC 111 peak, and then very beautiful streaking. This is direct proof that RHCP structure is together with its FCC. So within the single nanoparticle, we have two structures in it. And what does that mean? This is what believed. RHCP is a nanostable. So when we create nanoparticle using a supersonic jet, it's most likely this is the initial structure. But eventually, as a function of time, structural aging taking place, and it will end up with FCC. So we just picked up this part. Can we see this evolution? Yes. Just to do it, we have to change the place we see. So this is the last experiment and on this subject, and actually we changed the direction, the distance from the nozzle to the interaction point. So in this way, we change the time. And then this is what we expected of the single streaking. And this is RHCP. Then it should become mixture, and then RHCP may disappear. This is our prediction. And the experimental result is. And so far, as you can see, the experiment is last month, and this is from online analysis. So this is just powder diffraction. They could not find, still they are working on the data analysis, but it is already clear that RHCP structure decreases or disappearing as a function of the distance or as a function of time. This is a very slow time-resolved work we did. Okay, now let's go to the first one. We combine this technique with intense IR laser. And then we pump the nanocluster, which we described by the IR laser, and do the time-resolved work. In this case, what we can do is only to measure the shape of the black spot. We can't do anymore, simply because of the counting rate. But we can see, depending on the delay, the black spot becomes larger and weaker. So if we plot the intensity, it goes down, and if we plot the width, it goes up. But this is as we expected. Let's think that the cluster size becomes linearly small, becomes smaller and smaller as a function of time of the delay. By having this very simple model and estimating the intensity and width, this is what we get. So it is clear from the experiment that we are having the situation that the crystalline part becomes smaller and smaller as a function of time. And you may say this is ultra-fast melting or ultra-fast evaporation or whatever, ultra-fast disordering. But this is really the fact that the crystalline structure by itself is becoming smaller and smaller. And then the last question is, what decides this speed? And we did the experiment once again by changing IR intensity significantly. And then at that time, we measure the speed of ejected ions. And we could clearly see one-to-one correspondence of the shrinking speed of the nanoparticle and the ejecting speed of the ions. But in a sense, we knew it. If we go back to last century's very simple single 1D model of plasma, this is exactly what we expected. So what we found is the following. The shrinking speed of the crystal is practically the same as the speed of the ion ejection. That is practically the same as plasma sound speed. So what is going on is reflection wave is going into the cluster, and then the surface melts. This is exactly what we found. And the referee said, no, this should not be. And we have to work on a bit more, and we had to dig out all the data from L3S, where we made nanoplasma by hard X-ray and probe it by hard X-ray. And then we got exactly the same information as I described. So it really doesn't matter whether you make IR or XFL to make a plasma. Once you make a plasma, everything was decided. Okay, that is the first part. And now I'm an AMO scientist. I'm struggling that I can't do AMO with Sakura simply because of the limitation of the light. And that rescued, European XFL or Till Young and company rescued me. And now we wanted to see atomic motion using high rate FEL. And this is what I want to talk. So people know this setup. This was invented in Frankfurt group. This is cold rings. And they can image electron ions in a momentum resolved manner. We use ion part just to fix a molecule in space and then see the photoelectron in a fixed in space molecule, for this fixed in space molecule. That corresponds to photoelectron diffraction in the field of surface science. So this technique can be used as a time-resolved molecular photoelectron diffraction if it can combine with FEL, and this is exactly what Till and company did. And there is another way of making molecular movie, that is time-resolved Coulomb explosion, Coulomb explosion imaging. In the sense, both techniques are already established using synchrotron. We worked on this subject quite a lot, but the point is how to implement to FEL to get the temporal resolution. And I will be back in the comparison between those two techniques, but I want to go a bit more about photoelectron diffraction part. We normally take so-called polarization average to get the information, structural information. The trick is the following. If you have oxygen 1s or oxygen atom, and if you observe photoelectron from 1s orbital, this is what you get depending on the polarization direction. This is not what we don't want. And if we have carbon next to it, this is what we get. In order to get the structural information, it's by far better to take polarization average. Then this one becomes just ball, and this one becomes like that, and this one can capture the structure of CO. In this case, the distance of CO. And this is how it works. If you change the distance between C and O, and C oxygen 1s photoelectrons as a function of the distance, the pattern varies. First, you immediately notice that this is so-called forward scattering peak. The back scattering peak started to appear and disappear. This is the direct information of the change of the bond length. And so, if you plot the ratio of forward scattering peak and back scattering peak, this is what you get. And most of the people can immediately notice this is just exact signal. So you can get the bond length out of it. And surprisingly, although we have been playing with this kind of thing, when I arrived at the European XFL, Till and Ryan had grabbed my hand and explained what they observed, and they asked what they observed. And this was really photoelectron diffraction. I was so happy to see it. And the interesting point is that that was the last stage experiment of commissioning. And the sad part is that after that, the electron detector never worked. But anyhow, there is a data on oxygen, and what they observed is the following. There is oxygen in it, and then because FL is very intense, they ionize oxygen 1s, and then OJ decay takes place, and then molecular dissociation takes place, and then before it dissociates, the second photoionization takes place, and then OJ decay takes place. The key point is the second photoionization. The second photoionization has the information of this distance. And this is exactly what Till and company observed during the commissioning experiment. And using the sorry. So we made a very simple model. We just assumed Coulomb potential. If we assume Coulomb potential, we can correlate kinetic energy to the time, because we know Coulomb. And this is what Till and company got. I'm sorry, this is what Till and company got. Selecting kinetic energy, they estimate the internuclear distance. They change the internuclear distances, and then compared with ab initio calculation by Philip Demeskin's group. And as you can see, it is clear that this measurement observed the change of the bond length, even though there's no pump and probe. It is self-pump and probe experiment within a single pass. And as I say, I mean, this part was the case when we detected oxygen 1+ and oxygen 3+. If we use the channel of oxygen 2+, oxygen 3+, the corresponding photoelectron becomes broad, because it has a two component within it. The two components correspond to the case when, as you can see here, when the first photoionization causes one charges. This is one case, and the next case example is the first photoionization have a shake up. Then the energy is shifted about this amount, then you can separate those two components, and then if you plot the intensity ratio between forward and backward scattering, you can create series of oscillation, which I already showed from the theory side. And I think I could convince you that this technique can be used for determining the internuclear distances. And now the next question is this one. As I say, Coulomb explosion imaging is very, very strong. You can extract most of the information from Coulomb explosion. But quantitatively, Coulomb explosion imaging has some problem. This is what I'm showing here. This is a very nice, famous example of H2O, which Maria Novella already explained to you. And if you ionize oxygen 1s H2O, then OJ decay takes place, and then the H2O started to make anti-bend. Sometimes experimentally it is possible to reject overbend, but the problem here is the following. Because of the Coulomb explosion of the two hydrogen ions, the momentum experimentally determined is significantly far off from the geometric angle when the second ionization takes place. This is, in a sense, very well known, and this is how it is shown here. This is a real structure, and if you do Coulomb explosion imaging and make an average of such broad structures, you'll get this. So you never know the original structure or the angle. But by doing photoelectron diffraction, we can actually reconstruct the right angles, almost right angle. So this is what we expect to see. And in fact, this was the one which we were supposed to see during the beam time of Maria Novella, but unfortunately, once again, at that time, FEL did not work. Okay. At the European Expert, they have the tool to make double pulses, so we can really do real pump and probe experiment. And then my colleague, my friend, said, why don't you work on ethanol? He loves wine, by the way. But the reason why he suggested ethanol is because he already had the theoretical calculations. And it was really nice. And if you ionize, doubly ionize ethanol, the proton, hydrogen move to oxygen side, 1 or 2. And we should be able to measure it. The trick, the strongest point of Coulomb explosion imaging and photoelectron diffraction imaging is that it is very sensitive to hydrogen. If you use hard X-ray, you never know where is hydrogen. But this technique really proves the position of the hydrogen. Okay, anyhow, we wanted to see how it migrates. And this is the single trace, and you can clearly see where's the hydrogen, when hydrogen moved, and after hydrogen moved, still you can see where's hydrogen. Don't you think it is beautiful? But the problem here is that in order to show it, actually we use 2.5 kilo electron volt photoelectron energy. Unfortunately, TIL cannot do it. So we have to reduce kinetic energy to 100. So it becomes messy, but as long as we know what's going on, we can still identify and analyze this kind of structure. But another thing is that this is just a single trace, and in the experiment, we have to collect so many data, and from a theory side, they have to do many, many trajectory simulations, and this is not really enough, but what you can see is that the timing of the hydrogen migration is not a single time. This is around 20 femtoseconds or something. So if we take account of those distributions, this is what we get. And this is really what we can expect in the experiment. By changing the second delay, in principle, we should be able to follow the motion of the hydrogen here. not only for high energy photoelectron, but also even at 100 electron volt. You can see this part is moving. This corresponds to the motion of hydrogen migration. And we made proposal. The proposal was accepted twice, but as I said, electron detector never worked. We are waiting for the third. We submitted the same proposal. We will see what will happen. Okay, how much? 10 minutes? Okay. Okay, I spent too much. Okay, so Fermi, my favorite one. Now we wanted to steer the electron, and the trick is the following. If you are from laser lab experiment, it's a common sense. At Fermi, there are 6 undulator. You can tune the undulator to any harmonics of the seed laser. And as a result, for example, you can make omega to omega scheme, and you can tune the phase using phase shifter. So you can make this kind of field. Again, this is known in the lab using 400 nanometer and 800 nanometer, but the point is that we can do it in VUV. And as a result, as people are doing in the lab, we can do coherent control. We can swing the electron, the ejection of the electron. The direction of the electron can be controlled, for example. Did you see it? Should I repeat it? And we thought we should be able to find something more interesting. And we noticed this method can be used to extract the phase shift. And the reason, I'm a photonization person. I have been interested in phase shift during the photonization for 40 years. So finally, we got one of the new techniques. And the reason it becomes more fashionable is because this phase shift can be directly related to time delay of photonization. But the relation is just energy derivative. So yes, we can do it with this omega to omega scheme. And the experiment experiment by itself is relatively simple. The hardest part is how to create this light. But genius accelerator scientists can do it. We just need to measure it. And we use VMI to measure the angular distribution. And we selected those photoenergies for the demonstration of this experiment. And we use helium and neon mixed gas. So then, I'm an experimentalist, but I can even derive this kind of simple formula. This is helium. The ground state is S. If we ionize it by a single photon, we have P wave. If we have 2 photon process, we can get S and D. And the intermediate state is P. It is very good that we only have P. We don't have any confusion here. Then we can really write down S wave, P wave, D wave, and the phase shift correspond to those appears those. Phase shift for the S channel, P channel, and D channel, and optical phase difference. So simple. Student can do it. So, and then you can play with the equation, and then you get this kind of relationship. What we can measure from experiment is better. And now, I thought we could do complete experiment. Then, what I heard from the accelerator scientists is that they don't know this number. So they don't know the optical phase difference. Okay, then we can provide all those numbers because phase shift of SPD waves are known from the last centuries when I was young. So basically, using helium, we can completely characterize those double pulse structures. So the first thing we did is complete characterization of the double pulses. I was a bit surprised that PRL took it. I thought it should go to the more technical journal. And then knowing this is the result of the helium. As you can see, beta 3 oscillates and beta 1 as well, but we use this, and then you can see the oscillation. And then by just reading the difference here, you can get the information about this. So knowing the absolute phase now we know the phase. Thanks to hearing, we can do the same experiment of neon. The experiment itself is a mixed gas, so from the same experiment, we can extract the information of the neon. And then we got a problem because we wanted to do the same analysis, partial wave expansion, but it did not work simply because there are too many channels. So then my student said, Sensei means professor. What we are doing is to measure this. And what we can extract is the phase difference between single photon process and two photon process. That's all. I mean, sometimes students are much more smarter than very well-known professors, theoreticians. It's really amazing for me. You can see the list of the authors later. You will amuse that only one student noticed it, in spite of a series of famous theoreticians. But anyhow, this is what we got. So as a function of the phase, as a function of angle, the phase shift between single photon and two photon varies. And you see the experimental data point, and the curve looks like fitting, but this is ab initio calculations. It's complete agreement with theory. So the level of the calculation is the time-dependent Cassis shift. And the perturbation theory of another group gives right direction, but not quantitatively. But the good point of perturbation theory is the calculation is very simple, so we can get many more points. And you can see, based on this, we know what's happening here. We measure this curve here, and then after the resonance. So that's the reason why it increased and decreased. And originally, we thought because we measured phase shift, we can argue time delay between single photon process and two photon process, and we put these figures based on the two data points below this resonance. But the referee rejected this part, although they are very happy to our paper. So this figure disappeared from the paper, and the reason is twofold. Basically, we should have not used Wigner time delay. If we used Wigner time delay, people tend to believe we succeed to extract the delay from the single photon process. That's one thing. Another part is that, as I say, in the case of argon, neon, the initial 2p state is threefold. And what we did is taking the average of three channel, the phase shift of the three channel, and then made the energy derivative. This is the wrong way of doing. We have to measure separately for each channel, the time delay separately, and then you can take the average. So the referees are very good referees. Anyhow, this really goes to the last point. The reason why we are interested in that particular technique is because it is free from CC transitions. I mean, if we use rabbit technique, you always observe two photon processes, and at that time we thought we cannot separate CC transitions. That was the starting point, but working with Hans Jakob's group, I learned a lot, and at the very end, we succeeded to separate CC transition and single photon process. This is what I'm going to briefly talk to you at the very end. So it was really nice for me. At my arrival, they already have everything. They succeeded to create circularly polarized light, and they established how to characterize the path, and then they also established how to measure polarization, the degree of Stokes parameters. So I must say my contribution on this particular paper is very, very small, but still they are kind to invite me to this work. But what they did was to determine Stokes parameters and also at-scan resolved reconstruction of optical waveforms. So we know what kind of pulse we are using, and then this I already have some contribution. So what they did is the following. This is argon case, and they ionize it by the XUV, and then add IR pulse on top of it. It's rabbit, and then the interesting point is that they have circularly polarized XUV, and IR is also circularly polarized, co-rotating or counter-rotating. And so what they are doing is following. You create this or this and sum up of this. And my worry was the following. There are 3 components from P, but by selecting particular angles here, basically only one component is dominating. Then of course, this becomes like helium, because we can forget about the other 2. And then, by changing those helicity, eventually, by doing this kind of here this is the concept of the experiment, and they neglected one particular channel. So basically, this is based on propensity rule, but you can clearly see what kind of things you can measure, and you know what kind of equation you have to use to extract the information. And this is the result of the extraction. By using co-rotating and counter-rotating, they can really determine the amplitude and the phase. That means you completely characterize the vortex you made using 2 photon processes. You see? And then Meng and myself immediately notice, going back to helium, we should be able to finally separate CC tension and single photon process using the same technique. So as I say, it is possible to extract partial wave information. In this case, it's helium, so the intermediate state is only one. This really helps. And then by just taking the difference, sum of those 2, or taking the difference of those 2, we can get either beginner phase directly or mostly CC phase. These are tiny corrections, but this is exactly what we wanted to extract. But by having such kind of technique, we could finally separate. Yes, this is the last one. This is the last, and this finally we succeed to separate single photon process or Wigner time delay and CC delay. I mean, we made a round trip. I thought in order to have this complicated problem, we went to Fermi, but thanks to Hans Jakob and his colleague, I learned that this is much easier. And this is the end, but I wanted to show 2 more slides for my colleagues. There are so many H2O. And I got involved in VIX of H2O quite a lot nowadays somehow. This is a film, the subject is a film, substance of, this is H2O encaptured in C60. So the sample is thin film, but the spectrum look like just gas phase molecule. This was very, very beautiful example. And who asked the question? I forgot. But anyhow, the only difference is a slight shift of the vibrational frequency. But it is understandable, right? The potential curve is slightly distorted. We can clearly see such kind of thing. And this is for Aneta. This is real liquid water. And we are XFL people. We did this experiment, and we just measured, on this experiment, we just did Fresnel experiment. dependence. And I know there are so many discussions going on of this double peak structure. I'm a very freshman. I don't want to listen. Sorry. I wanted to, together with Hans Jakob and Robin Santora, basically wanted to put some new insight on this particular subject. So we decided to take fluence dependence of water molecules, liquid water, and this is the result. And what you can see here is by increasing the fluence, basically you are killing this peak, and satellite structure appears. And we also did IR pump and probe experiment, and this is still under analysis. And this is for John, who could not make it. And once we finish all the analysis, please invite John on this subject. Thank you very much for your attention.
Thank you so much, Kiyoshi, for this very broad scientific interest in many domains, using many photon sources, many techniques, many theory. Do we have some questions? Arnaldo.
Yes, well, it's a simple question. You showed this angular distribution taken at 100 eV, but you show that if you take it with a much higher energy, this angular distribution, you can get the atoms much easier, right? So, question is, so do you see a foreseen future that you could, well, some facilities that can actually do the real experiment with the higher energy?
So the question was whether we can detect higher photoelectron energy or what? On which subject possible?
Time dependent. I think it was the GFSB, I think, on CO, the prediction, theoretical predictions on how the molecular frame photoelectron angular distribution was changing with the time.
Here we lost it. In the case later, in the case, okay, it's not CO2. So, in the case of ethanol, we did we did the calculation at 100 electron volt and 2.0 kilovolt.
Yes.
2 kilovolt correspond to the the wavelengths correspond to that kinetic energy correspond to the 1 Angstrom divide.
Yes. So my question is, if you foresee in the future to be able to do the experiment at this 1,000 EV instead of 100.
Such kind of a discussion is in fact going on. If you ask now to tell, the answer was no, because of the setup. But certainly, I mean, there is one very crazy person who wanted to use Cortum's type technique to more than 10 kilovolt. And he was really seriously talking to Heidelberg team. And of course, it becomes a giant structure. They need a huge amount of magnets. So superconducting magnet, Cortum, or whatever. So we should be happy with 100 electron volt.
Other questions? If not, we can really see that you are interesting more and more to short, to ultra-fast dynamics in the attoseconds time range. And we also know that LCLS now can have ultra short pulses. So how do you see the tendency, the future of our domain using this kind of technique with ultra short pulses with high intensity?
Thank you very much for asking this question. First of all, I came from photonization field. And so what I had been doing for a long time was really a direct relevance to photonization time delay. That's the reason why I was so happy working with colleagues in Hans Jacob's group. Then our interest was completely overlapped, and I could put my old knowledge to such kind of new things. But also, as you pointed out, I skipped that part because there are so many talks on LCS. And another subject which I have been very much interested in it is really to see the motion of electron, charge migration, or to be more exact, how first charge migration takes place, but of course nuclear motion follow up. That was completely opposite way of what we learned from the textbook. You see, when you go back to the old textbook, the molecule moves and the electron follows. But nowadays, those guys make the electronic wave packet and it really moves and then nucleus should follow. And this is exactly what's going on at LCS and other lab, at Scan Lab. And I have been very much fascinated in that direction, partly because in the case of photonization time delay, it's a sort of fun. But in the case of charge migration or controlling such kind of electronic wave packet, it may make a future of controlling reactions. So I think this is a kind of dream, and I'm pretty sure, for example, James is willing to talk about such kind of directions, if I understand it. James, right?
James seems to approve. Other questions? If not, I think we thank you very much, Kiyoshi.
Thank you. So when should I take it now or? Maybe after we break. Okay, thank you very much. There's no rush now. Yes. So what the theory was doing is somehow heating up the sun. But we know very long-standing discussions